I got 55.9.
Very good. And for chloride, Ibrahim? Okay. We'll go back to
What is Z again?
Huh?
What is Z again?
The valence of the ion. Whatever C. C is an ion. We calculate, and this is equation 3.21 in the text. And it was on page, I can't remember, it's in chapter 3.
59.
On page 59. And so, if you forget, check the text. I always check the text anyway. I could get it wrong. Do my best to make sure I'm giving you accurate information. But part of having a college education is being critical of the information that comes at you, so that you don't blindly believe whatever you read on a web page or whatever you hear on a cable news show, for instance. But no, you're going to be experts in the field of engineering. You need to be able to critically evaluate information and to think critically. I was just talking to Dr. Penley the other day, and he told me that this is what he does. He teaches people to think. Is that true?
Mm-hmm. I've been to his classes. It's great.
Is it 6.96?
Say again?
6.96?
6.96, that's right. How'd you get it?
So RT over F is going to be 25.8, correct?
25.8 what?
No, that's
Millivolts?
you multiplied by. That's not millivolts. It's
Say again?
Millivolts?
RT over F will be millivolts if we, it will be volts, but if we multiply by 1,000.
okay.
So if you get RT over F, you'll get 0.0258 volts, which is the same thing as 25.8 millivolts. They often convert it when dealing with Hodgkin and Huxley stuff, because that's what Hodgkin and Huxley were measuring on their oscilloscopes. Now, so that is a good value for RTF. It's really, it's not exactly 25.8, it's 25.77 because it's 299 instead of 300. Not as important in this question, but in another question, if the temperature is 6 degrees, then you're going to be off by several millivolts, and no need for that. Just calculate the RTF. So that's the RTF, and so what's the rest of it?
Chloride has 7 valence electrons.
Huh?
Chloride has 7 valence electrons.
No, okay, yeah, that's a confusing thing. There is a valence from molecular orbital theory, but there's also a valence from basic chemistry, which is just sodium has a valence of +1, because that's the charge on the ion, and chlorine has a valence of -1.
Okay.
So that could be part of why you got the wrong answer. So you have a -1. So minus RT over F. This is going to just cancel and give you a plus. And then you have an ln of what two values?
18 over 120.
18 over 120. So
Would it be 48.94?
I got a negative.
48.94. I would take off a point for that. Why?
It should be negative.
Yes. This logarithm, whenever the number inside the logarithm is less than 1, then the logarithm will be negative. If it's greater than 1, then the logarithm will be positive. If it's equal to 1, the logarithm will be 0. That's right. So 18 over 120. And this will give us minus, say it again. You ready?
48.94.
48.9. I'll just do the 1 decimal. Okay. So that's the first part of the problem, is to get those voltages. Okay? Now what's the second part of the problem? Assume that you can do what? Somebody read it to me, please.
Modify the membrane conductance.
Membrane conductance for
Fully ions from 0.
potassium, sodium, and chlorine from 0 to infinity. So, GK can go from 0 to infinity. GNA, 0 to infinity. CL, 0 to infinity. So, how is that going to affect the transmembrane voltage? They're asking for the maximum range of membrane voltages. Many of you just took some numbers from down here and subtracted and gave me a value. And I took points off if that's all you did, because you didn't show me your reasoning. Even if you got the right thing, I want to know why. So, what relation do we use to determine the membrane voltage when you have multiple ions? What's it called? Where can we find it in the book? Got it, Hayden?
We're looking at the currents from the conductance one.
It is a parallel conductance model. It's on page 65. It's equation 331. Transmembrane voltages. And if you look beneath the equation, it's the steady state parallel conductance equation for the resting transmembrane potential and the steady state constraints. That's what the title of this section is. And it says that this voltage is equal to may call the chlorine a leakage current. No, it's called chlorine. So, by the way, what are the units of the numerator of that equation? Numerator is the sum of these three quantities. What units will that sum have? Or what dimensions, rather? What dimension will it have?
Just the top?
Huh?
Just the top?
Energy, you're thinking in the right direction. That's not the right answer, but what did you say, Ibrahim?
Is it just the top of it?
Yes, the numerator. Numerator, denominator. Denominator, what's the units of the denominator?
Is it just
Conductance.
MS divided?
Conductance. What's the units?
Voltage.
So you could say it's,
Current.
Voltage
Oh, it's
times
voltage
conductance.
times
you're right, but what did you say?
Current.
Current. Why current?
Because it's the conductance times
Current, yes.
the
Okay.
potential.
What's Ohm's law?
E equals IR.
Yes. In terms of dimensions? Voltage equals current times resistance. V equals IR. Now, when we deal with conductances,
1/1.
it's 1 over R. So we can say a conductance times a voltage, call it E here for electromotive force. They're using just a different symbol. It's confusing, but if you know what it means, it's not. This is another equivalent way of writing Ohm's law. Conductance times a voltage equals a current. So if you understand Ohm's law really well, you just look at this and you go, oh, that's a current. I mean, it's a value, its value is a current. All right. Now, to the reasoning for this question, which is what you need to do if you want to get full credit for this question. What is the maximum range of transmembrane voltages that you can achieve by such a tuning? It says a tuning, as I can set these to be anything I want within these ranges. So if I want this value, this V of M, to be maximum, what would I have to do? Got these values for the E's and K's. The EKs, the EK and the E's. Got these values for the E's. And I can have any value I want for the G's within this range. Which setting for the G's gives me the maximum VM, and which setting gives me the minimum? Huh?
The minimum would be if you make the denominator bigger, because that'll be 0.
Well, if you make the denominator bigger, well then all these get bigger. Yeah, I mean, so if you make this like infinite, well then these numbers will also be really big. So that doesn't help us so much. What some people did to get full credit was they said for the maximum, I want the sodium is the thing that makes it positive. I want that to be as high as possible, so I'll say G of sodium is infinity. And G of K, what effect would the potassium or the chloride have on that? If you're trying to make it, what effect would it have on the voltage?
It'd make it lower.
It would lower it. So what can I do to the conductances there? Yes, I set those conductances to 0. And then we get, this becomes essentially what? This will just be G and A. We have G and A times E and A over G and A. Now we're saying this is infinity, but we really mean we're just making it as large and larger and larger. So as we do that, this cancels out, and that's the maximum we can get. So if you did that to explain why this is the maximum possible voltage, and then what's the minimum going to be?
Where the sodium conductance is 0, the other two are infinite?
No.
The potassium is the determinant,
Yes,
so make that infinity and the other 0.
that's right. So you were close, Hayden. You would have gotten nearly full credit if you had said that. Because at least you're doing the reasoning. And so that's why some of you correctly said that the range is this minus this. Some of you correctly said that, but without any reasoning. I took off a couple of points. And this